Next up, Steve Bible with a SuitSat 2 update. So I get to introduce myself. How's that? How many of you know about SuitSat 1? Okay, just about everybody here. Here's SuitSat 1 merrily having just been deployed, and it posed for us so we could take this snapshot. And it was quite an exciting day that couple of years ago. Here's SuitSat 1 that's been outfitted with the equipment that we put together many years ago. Very simple mission, mostly because we only had a very small amount of time. It actually was, we had hoped to put packet radio on it, put a camera, but as it was, with a short amount of time, the sole mission that it had was basically the voice, which had the commemorative messages and also the messages from the school children from around the world. And here it is. It's already been assembled, and now it's tucked in the corner getting ready for the day it'll get deployed. You'll notice on the top the antenna, of course it's folded over. It's recognizable because it's the ARRSSAT way of making an antenna using this steel that is normally used in a tape ruler. On top is a switch box, a safety box. Basically, it has an on-off switch. There's 3 toggle switches there. One is for on-off, power on-off, and then to enable 2 timers because we wanted to make sure that SuitSat did not transmit for about 8 minutes, giving it a chance to get deployed away from the astronaut and cosmonaut and not cause any RF transmission in their vicinity. The equipment was actually in the waist section. If you look carefully, you'll see here the arms. Basically, the cable comes down and it goes up the arm and then inside the suit itself. On the outside of the suit is a patch and a CD-ROM with artwork from school kids around the world. What's unique about this Russian Orlan spacesuit is that it's a one-size-fits-all suit. The Russian cosmonauts, in order to be in the Russian space agency, you actually have to be a certain size. Whereas in the United States, I think they have small, medium, and large spacesuits. Now, the only thing that changes about the Orlan spacesuit is actually the gloves. The gloves actually have a kind of a rotating cuff and then it unlinks. So you can choose a small, medium, or large glove. Well, what we discovered in putting SuitSat together is we needed a way to route the cables which were mounted on the helmet into the electronics which was inside the waist of the suit. So we discovered we could just take the glove off and then it becomes basically a conduit. All right, so for SuitSat 2, here's what we're working towards. Again, the voice messages that'll be transmitted down, regular FM. It'll be transmitted down on 2 meters. I'll show you the band plan here in a moment. We also hope to create a linear transponder where you can actually talk through it using single sideband. It would have a CW signal coming down. We kind of talking about commemorative call signs, messages. In other words, let's transmit CW, get kids interested in CW, decoding it. Work on regular FM packet. The packet would be, and of course a lot of what it's going to be transmitting is still yet to be determined, but the thought on the packet would be for telemetry. Now, one of the things that we're hoping to do is create a package where we can attach experiments to it. This way, as the Orlan spacesuits are going out of service and become available to us, then SuitSat 3, SuitSat 4, that sort of thing would be different. It would be the same electronics, but it would be different because different experiments could be attached to it. So we're trying to create a baseline set of hardware that will be proven, tested, and accepted from the safety officials in NASA and Russia. And this way it'll be very easy to build up the electronics and pass it on to them for each of the missions. I should say that the Russian philosophy with their spacesuits, their Orlan spacesuits, is they discard them after 5 years or 12 wearings. Okay? The United States philosophy is you bring it back down on the shuttle, refurbish it, and then send it back up. So what's interesting here is that we've kind of have a steady stream of spacesuits. Pretty cool, right? We're talking about telemetry and the form of packet, and it would be telemetry not only of the battery voltage. We're planning to deploy a lot of temperature sensors throughout the suit, and the telemetry for the experiments. And then we're also talking about, we would have a 400 baud BPSK. This is a la Oscar 40, Oscar 13 type of BPSK telemetry. So you would just need a single sideband radio and then a sound card program, and you'd be able to decode it. And then we're talking about putting 4 cameras on it, each facing a different direction. We would do a picture capture, format it into slow scan TV, and then transmit it down. So let me show you some of the hardware that we've got together. Well, first of all, you got to have a meeting. And we've had several meetings. I think you'll recognize some faces here. This is Lou McFadden. Lou McFadden is the hardware manager for ARISS, amateur radio on the International Space Station. Here is Frank Bauer, who is the chairman of ARISS. ARISS is an international organization represented by each of the countries that's involved with the International Space Station, which is the United States, Russia, Canada, the European Space Agency, Japan. Have I missed anybody? I think that's it. So he's the chairman overall of ARISS, and what the people that make up ARISS are basically from each of these countries, representing what is going to be amateur radio missions on the International Space Station. And you probably noticed in the news recently that Owen Garrett's son is going to be a citizen visitor to the International Space Station, and he's a ham. So you can see there's a bit of a flurry of ARISS activity coming up. Here is the back side. I should get a better picture. This is Sergei Sambarov. Sergei, of course, is representing Russia, and it was Sergei's idea for SuitSat in the very beginning. It was at the AMSAT meeting that was in Washington, D.C. He knew that the Orlan spacesuit was going out of service and had this idea of putting electronics in it. And it was very quickly, right after that, dubbed SuitSat, and that name has stuck ever since. This is Kenneth Ransom. Kenneth, you probably noticed, is very active in ARISS. He's one of the ones that coordinates a lot of the activities on the International Space Station. He's based out of NASA Houston, whereas Frank is based out of NASA Goddard in Maryland, and Lou is retired from NASA. This is Joe Julisher, good friend of mine, and we worked together at the same company, and we worked on SuitSat 1 together, and we're working on SuitSat 2, and we've managed to rope in quite a few other characters at work to help play in this sandbox. If you were at Dayton just this year, here was the demonstration of some of the equipment. Here we have the software-defined transponder board, and I'll show you a close-up picture of this later. And here is the proposed antenna, and I'll have another picture of it here later on. And then off to the corner in blue here is the switch box. It's the same switch box as for SuitSat 1, again, doing the same functions of turning it on or off and then enabling the 2 timers for safety. What you see here in the middle are basically an up converter, down converter. What the software-defined transponder is doing is it's at a 10.7 megahertz IF. So these 2 boxes are down east microwave transverters that have been modified such that they'll take the 10.7 and then for the transmit up convert it to 145 megahertz, and then for the receive take 435 megahertz and down convert it. So this was actually operational at Dayton this year. And the antenna here, we'll notice the long element here is for 2 meters and the short elements here are for 440. So this is setting up what is the linear transponder for SuitSat 2. Here's another picture from another angle. It shows you the switch box. Curious thing, notice that it's blue. When you paint something, this is kind of, I guess this is how the space industry does it. If you paint something blue, it's not meant for flight. It's the ground experiment. When you paint it white, that's the one that's meant for flight. So they kind of color code things, so it's kind of cool. Here you can see the antenna a little bit better. Notice there's kind of this Delron cup that's been milled out to allow the antennas to flare out. And again, it's made out of the same material that a ruler, a metal tape rule is made. And I'm going to show you a picture later on. The idea is that they can be folded and then put a piece of Velcro around it to kind of bundle it up so that they can get SuitSat through the airlock and then let go of it and it'll deploy itself. Now, if this is the proposed band plan, you can see that we've got the 2 meters and the 70 centimeters here. So the uplink would be all sideband to provide a transponder so you can communicate through SuitSat. And of course, SuitSat's going to be in a very low orbit. As you probably know, the International Space Station is only 250 kilometers up, which is quite low from a satellite standards. And if you've ever watched the International Space Station go across the sky, when you get the opportunity for the sun to reflect off of it, you can see it looks like a speeding bullet. Well, imagine trying to communicate with a satellite that's doing the same thing. And also I've had the opportunity to do an ARISSAT contact with an elementary school in Tempe, Arizona. And we had a very good pass, but even if you have the best pass, which is just straight overhead, it's about 9 to 10 minutes. And of course, as SuitSat is deployed, it's deployed intentionally toward the Earth so that it comes down and eventually burns up. So the orbit just gets tighter and tighter and tighter, and it's quicker and quicker and quicker as you come across. So here you go. You'll notice that we've got the CWID, then we've got basically the FM and the packet on this side. So this is what we're working toward with the software-defined transponder. So introduce the software-defined transponder. I think this is a term coined by, I don't know, probably Bob McGuire or Tom Clark. We'll have to ask him when he gets here later. The idea is we're using kind of software-defined radio, but we're going to use it in a transponder aspect. What we're going to do is up on the helmet will be the antenna and the cameras, and then we're going to have the 2 meters to 70 centimeters transmitter and receiver, which will be up on the helmet, and then the coax from the helmet to the electronics that's inside the waist section will be 10.7 megahertz. And then the software-defined transponder will be inside the belly of the suit. And here you can see this is kind of a breakdown of the components that's on the circuit board. Here's a block diagram, and for those of you that have probably read Gerald Youngblood's Software-Defined Radio for the Masses, this looks very familiar. And this is taking a 10.7, what we'll call an IF in and IF out, where you have the quadrature sampling detector and the quadrature sampling exciter going into an audio codec, and then we're putting it into a digital signal processor, and then through an SPI serial port, we're sending that off to the processor that is to be the internal housekeeping unit. The idea here is the programming in this digital signal processor then is the whole software-defined radio aspect. It does the transponding, it does the filtering, it does the FM, the sideband, and the CW, and the BPSK. And here's the hardware. This is the second generation board. This is the board that you saw in that photograph from the Dayton photograph. This is the board that was actually operating. I should say we made 7 of these boards, so it was one of those 7. Here you've got the digital signal processor. Here you've got the codec. And then you've got the, let's see, this is the IF out. So this is the quadrature sampling exciter here, and this is the quadrature sampling detector. So it comes in here, transformer. This does the switching and the sampling, sends it off into the codec and then digitally into the digital signal processor. Then we go through an isolation device here and then into this connector. This is the SPI port, which will connect to the IHU. This port here is for an Agilent logic analyzer. It's wired up for this logic analyzer probe, so we can plug it straight in there and watch our signals. These are power supply switchers. The 12 volts comes in. This one breaks it down, first of all, to plus and minus 9 volts, which then gets regulated and filtered to plus and minus 6 volts, and then sent up to the op amps that are up here. This switches from 12 to 5 volts and then gets changed to 3.3 volts digital and analog. And I can talk more about the design of this board because I did it. This one here, and if you're interested, we can take that offline. The internal housekeeping units is designed by Joe Julischer, N9WXU, and here's a block diagram of it. The idea is it'll have a central microcontroller, and here's the SPI port to the software-defined transponder. Then there's going to be an I2C port going off to the power supply board. I'm going to show you a photograph of that just in a few moments. We're going to put an SD card on it, and this is what's going to hold all of the voice. Whereas SuitSat 1, we took the voice, digitized it, and put it into a serial flash. Basically, that's what an SD card is. It's a serial flash, and we'll talk to it through an SPI port. The idea is now we can take the voices, download them to the computer, reformat them, plug the SD card into the computer, drag and drop them, unplug them, plug them into the IHU board here, and we're ready to go. That's the idea. Okay, we still got to pull that off. Now, what's interesting here, these RS-485 ports are to the experiments, and what we're doing is we're providing 4 of these ports. We're also providing 5 volts, and then we're basically turning the experiment on, allowing it to do its thing, transmit its telemetry, and then we're going to shut it off. We're trying to, of course, control each aspect of the satellite for power savings. And we've published this protocol, and what we've done is we've created little circuit boards which you can build your experiment on, and then we even have the little box for it, so you can, it's almost like we're going to give you, the skeleton, the circuit board, the box. Here, just build your experiment in here, and then give it to us, and then we'll plug it in, and it'll talk to the IHU. The IHU will then take that telemetry, format it into the telemetry stream, and then send it down. Okay, now let's go off here to the left where you see the FPGA, this serial RAM, and this video input processor. What we did is we found this chip that will take 4 channels of NTSC video, and it's normally for what you would call fast scan video, regular NTSC video. But what we wanted to do was take that video, take a full scan, and store it to this serial RAM. Well, what we do is we have another fellow by the name of Jerry Zdenek, and Jerry is programming this FPGA to take this output, format it into the RAM, and then the microcontroller then through the FPGA addresses this RAM and looks at it and looks at its luminous and sees, okay, is it all white or is it all black? Meaning, do we even have a legitimate picture? Because SuitSat's going to tumble. SuitSat 1 definitely tumbled. We're expecting that. That's why we got 4 cameras on it. We want to snap a picture and know that we've got a picture before we take the time to transmit it down. Slow scan TV takes 36 seconds to transmit 1 image, and it would really be a bummer if you just transmit all black.
No stars?
We would hope there would be stars. So it's all stars, Dave. I'm glad you all got that. But anyway, this is quite a project in and of itself here, and the high altitude balloon people are really excited about this part of the circuitry. Okay, so we're trying to provide them. I'll show you the progress that we're doing along the lines for that. So this is kind of neat. Here is a picture of the IHU. This is the 2nd generation IHU, and what you're seeing here's the microcontroller. Then, of course, there's power controls, power conditioning on here. What you're seeing is that when we took this picture, we didn't populate the FPGA, and this is the serial RAM here, and this footprint is for that video capture. And so far, we of course have populated the rest of this board. I'm kind of curious why we didn't take a picture of a fully populated board. But we've got this circuitry working partially, and then we've got to write the code in the microcontroller that'll read that video scan and turn it into slow scan TV. Sure. What microcontroller on here? This particular microcontroller, this is a microchip PIC 24. And what we're going to do is I'm going to show you a picture here of, this is 3rd generation. And as you can tell, this is kind of a snapshot from a CAD program. We've not fabricated this board, but we're going to move to the PIC 32, which is a 32-bit processor. Now, it's a bit difficult to, especially from my angle here, but the serial RAM, FPGA here, man, it's real hard from my angle. The thing I want you to take away from this is, of course, it's hard to see the dimensions on this. This board's probably 8 inches by 8 inches. And of course, as we're learning, this one's 3.75 by 3.5, and we still got some room down here. So we're learning, and we're able to kind of shrink it, because one of the things that we were kind of curious with is if we could end up making some hardware that the CubeSat people would be interested in. And the CubeSat people are, down to this size. It's almost like a PC 104 type of form factor. But the one thing that the CubeSat people are really struggling with is power consumption. I won't call it a struggle, but if you could imagine, when you're talking about a little cube that's about 4 inches on a side, there's not a lot of surface area for solar panels. And then, of course, there's not a whole lot of volume inside it for batteries. So everything that you design, I should say, around the CubeSat has to be incredibly power efficient. And I won't say that ours is incredibly power efficient, but as we learn, we're trying our best to keep ours as power efficient as well. So let's move on now. See this little hole here, this little hole here, that little hole there. The idea that we're having is this is where this box, which has houses the antenna on top of it, and also will house the transmitter and receiver, will also house the 4 cameras. Okay? There is a hope to try to snap a picture as it's being pushed away, and of course we're working toward that goal, but you heard it here first, but if you don't see it, don't blame me. There's still a lot of unknowns here. We're still doing a lot of development here and asking a lot of questions. So this is to show you that the idea is that we would have the cameras up on the helmet. Now, in designing this equipment, we have to design it in such a way that the astronaut and cosmonaut are going to assemble this. So we got to provide instructions. So naturally, we want this to be as simple as possible to assemble. So think in those terms. You can see why we're putting the camera up here, because we're trying to keep, okay, there's bolt this on head, put inside stomach, wire in between, and push out door. And then we write that all in Russian. But, I mean, you get the point. We got to make this thing incredibly simple for them to assemble. Okay? Now, here's some camera images. This is to credit Jerry's house. This is Jerry's. So what you're seeing here is basically Jerry managed to get the FPGA programmed up to where it actually took the NTSC scan and put it into the memory. And what you're seeing here is a memory dump. So this is not a slow scan image, it's actually the memory dump, which is just a significant step. And that we're controlling the video chip, we're getting it into the RAM. Now the next step is for the microcontroller to address the RAM, extract only what it needs and formats a slow scan image, and then of course sends down the tones, which will be the slow scan image, and then you'll be able to receive it and decode it. So here we're getting to see Jerry's backyard and his laboratory. I don't know if he really realized that once he took these pictures, the rest of the world was going to see them. But this is quite an exciting step. The power supply unit, so this is kind of a concept. We're going to try, get this, we're going to try to put solar panels on the suit. Now what's interesting about SuitSat is that an Orlan spacesuit was made for one thing, for a person to be inside it. It was not made to be a science experiment of putting electronics in it. So the suit's not made to bolt solar panels on. So we're really, this is kind of a concept where you can see it's kind of a trifold. The idea is that 2 of these will fold up for a total of 6 solar panels, but the idea is for them to fold, put the vulnerable side of the surface of the solar panels inside so that they can be shipped up to the International Space Station, and also kind of easy to, okay, step 1, strap to leg with Velcro, open up panels, and we're trying to get it to where, okay, it's easy to install, and the idea is, okay, it'll go around the legs. That's the idea today. It may change. Open them up, and open them up in such a way that we're trying to get the panels to cover all angles, as many angles as possible, because the suit will tumble, and we're not going to get full illumination on all 6 of them. And as best we can so that the sun is hitting at least one of them, and that way we can get some power from it. So we're calculating basically our power budget, and naturally to say, if you only got one panel illuminated, you don't have that much power. So that's what you have to work with. But the nice thing will be, of course, SuitSat 1 lasted 2 weeks just on 3 batteries, and that was it. Mission over. This time with the solar panels, at least we'll be able to have fun with it for a couple of months. What we hope it would be several months. Now, how are we going to do that? So one of our other engineers at work, oh good, it didn't. That's cute. Okay. There was supposed to be a graphic here of a block diagram. That block diagram was showing the circuitry of this little block right here. And notice you'll see the same block 6 times. This is a max power solar converter circuit that John Charez designed. And the neat thing about doing SuitSat at work for the fun of it is then you get to publish articles and application notes on the work that you did. So if you go up to the Microchip website and download application note AN1211, you can read about this whole circuit here. The idea is that as the illumination and the temperature of the solar panel change, so does the knee of the curve where you want to be changes. Each of these 6 converters here have its own microcontroller, so it's actually very smart in detecting where that curve is and delivering to the bus the max power. So this is quite an interesting circuit here, and it's quite exciting. And this circuit does work, and we're going to fly this. Now, what you don't see here on the bottom side, on this side, are voltage regulators, and here's another microcontroller which is basically communicating with all of these so that we can get status from them. Each of these max solar power converters is autonomous, independent autonomous. But what we want to do is collect data from them, and then that data will be sent down in the telemetry stream. And we would be able to see things like, okay, how's this one particular panel doing? What kind of current is going through it? And then these are switches that switch power to the experiments, to the cameras. Antennas. So this is a picture you saw earlier. So this kind of shows you the form factor. Again, this box here housing the cameras and the transmitter and receiver. So now you can kind of see a little bit of method to the madness. If we put the 2 meter and 440 transmitter and receiver up here as close to the antenna as possible, then we don't worry about any cable losses. So the only cable losses we got to deal with are at 10.7 megs. And then we can control that. That's not a weak signal. We can amplify that from an IF perspective. And then the antenna, this time being designed and tested, this has actually been tested on the top of a step ladder. You know, step ladder simulates a suit very well. Who would know? And antenna here is working real well at 2 meters and 440, so this is what we're planning to fly. And again, this is, of course, what we demonstrated at Dayton this past year. And here's a picture of basically taking the antenna, folding it up, and using a piece of Velcro. And of course, this is so that as the suit is being taken through the airlock with the astronaut and cosmonaut going out for an EVA, then it's not sticking out all over the place like Marvin the Martian. Okay, and probably the slides that I realized that I missed here are on the experiments. But the experiments are basically based on a protocol that'll be RS-485, and what we'll provide to the people who are doing the experiments will be kind of almost like a little demo board that's already programmed up with the communications back and forth to allow people to really concentrate on the experiment themselves and not have to worry so much about it. And we're going to power it up and power it down. We already have some people that want to have power all the time. Well, we just don't know enough about our power budget on this particular one. What we hope to accomplish, of course, is to get all of this equipment working. This is a very ambitious program to get all of the electronics. Because you can see we've got a lot of hardware. What's lacking is a lot of software. And we've got also next generation hardware that we're already contemplating that'll be shrunk down and also be in a form factor where we can stack everything. And yes, the balloonist and the high altitude balloonist are very fascinated with a lot of the equipment we can do. As you can imagine, except for the power supply unit, everything else there could be launched on a high altitude balloon. So we're working with them as well because they make for a test platform. We already launched the slow scan, first generation slow scan. We launched that on a high altitude balloon by a Texas group, Doug Loffmiller. And all it was transmitting was a test pattern, but it gave us an idea that, hey, yeah, slow scan TV can be used for a high altitude balloon.
I noticed that in the Scouter magazine that I get, that there's a Cub Scout pack and some other Boy Scout pack, or troops and ventures that are working on this project with you guys. I was wondering if you could give us some information on their function in this.
Right. What you probably, there was an article in Boys Life. Is that?
No,
it was
Adult Scouter.
Okay, the Adult Scouter. So what they did is it was also in Boys Life. Well, here's what we did. Joe is a Cub master, pack master or Cub master in Maricopa, Arizona. So we got this. We're always trying to find twists and turns of how we can get kids involved in this, and of course work on the publicity for this. So what we did is we built up the safety box and made it kind of a kit, and then we had a pack day, which was on a Saturday, which was a space theme. So the kids did, launch bottle rockets and did a skit. It was a really cute skit. They were coming through this cardboard International Space Station and deploying SuitSat. It was cute. It was real cute. And what we did is we had two tables there where we had soldering irons, we had the wire there, we had the screwdriver, and we just had the kids coming through, each of them getting an opportunity to plug in a wire, solder a wire, or put in a screw. And we had the Boys Life photographer out there snapping pictures, and they wrote that article. So we got the kids involved that way.
Can you describe how that box attaches to the
helmet? Sure.
Because you could see there was some fittings and things, but it really wasn't clear how you actually physically attach that to something that wasn't designed for it.
Well, it was interesting. When we did SuitSat 1, we all met in Houston, and then we went onto the NASA grounds, and we went to the manned spaceflight building, and there they actually had a suit. And we were all over that suit, taking pictures, had rulers, because we were trying to figure out, okay, how are we going to do this? Well, what we discovered is the helmet, what you're seeing on that helmet is kind of a fiberglass overcoat. But what's inside it is a great big glass fish bowl with no fish. But that is, of course, the vacuum. And there's the sun visor in the front. And so what happens is the cosmonaut's head, moves around in this glass bowl. Well, if you want to look up, what they did is they put a little sunroof up here. And the cool thing is that there was a bezel that screwed on there holding a sun shield. So we're like, great, they were thinking of us, So what we did is we figured out we could remove those 4 screws, take the bezel off and the sunscreen off, and then that bracket was made by the Russian side of ARRISSAT and fit those 4 screws and then screwed it down.
So you actually have a permanent hard point. You're not like Velcroing it on?
No, it's a permanent hard point right there. I mean, it's very stable. And then the only other thing was, okay, how do we get the cables inside? And of course, like I said, we noticed the glove on that, so that got the cables inside.
Steve, I was just wondering if you take and fill that suit up with crunched up newspaper to give it some body.
It was basically old clothing they stuffed it with. See, normally the Progress is the supply ship that goes up. And then once they unload it, then it becomes a space dempsey dumpster. And then they fill it with trash, and then before the next Progress comes up, they detach it, comes down and burns up. Well, SuitSat kind of, okay, here's an opportunity to also get rid of some trash. So that's how they did that.
So it's underwear with skid marks in it.
Let's not go there. Remember, we're recording a DVD here.
Okay. The other question I have is that do you put any conformal coating on any of the PC boards?
Yeah, we did. We coated the boards.
Okay.
Mm-hmm. And we didn't go through real strict AMSAT and NASA, of course, we used some good engineering practices. We had to be careful of certain materials. You know, glues were out of the question. You had to use approved paints and all of those kinds of practices. But it's a very short-lived mission. It's not like you're trying to design a satellite to operate for years. Okay? Well, that's about all we have time for. I can catch your questions. It's time for lunch, unless you want to stay here through lunch, since I'm the one making sure that we're staying on time here. But thank you very much for that.